Okay, and we're just going to look at linear transformations. Now, basically, linear transformations have to follow two rules that the transformation on x plus y must equal the transformation on x plus the transformation on y, and that the transformation on some lambda times x or some scalar multiple of x must equal the scalar multiple times the transformation of x. And that sounds really difficult, but in lots of ways it's not too bad. The origin must stay the same. For linear transformations, the origin must stay the same, and that's always a nice one to check, especially if you have to prove that it's not a linear transformation. So basically, if we were to make a linear transformation on this axis, these are the standard axes, the new axis might look something like this, where that becomes your y-axis, say, and your x-axis might come out here. So that would be a linear transformation, and all we've done is squish things up a bit. So there's our new axes, and our new coordinates would be the same sort of situation where our coordinate grid would look something like that. But let's look at an example, because that might make it a bit easier to understand. So let's look at this transformation. So this is the transformation. x1, x2, x3 becomes x1 plus 2x2, x2 plus 3x3, and x3 minus 1. So what happens to this point here, 8 to 4? Well, 8.24 under this transformation becomes, what does it become? It becomes 8 plus 2 times 2 is 4. So this becomes 8 plus 4. This becomes x2 becomes x2 plus 3x3. So 2 plus 12. And x3 becomes x3 minus x1, so 4 minus 8. So after the transformation, it equals 12, 14 minus 4. And that's all it is. We've taken this point and we've transformed it onto here. So let's look at those two rules that I had before, these rules. For it to be a linear transformation, number one, well, you could check 0, 0, 0. So, but you're going to get 0 plus 2 times 0. Yep, that stays as 0, 0, yep. So they stay as 0. But let's see what happens to, instead of this, let's suppose we had x was 6, 1, 3, and y was, in this case, 2, 1, 1. So that should equal exactly, if this is a linear, we should get this as an output. This should be our output if we just do the transformation and then add. Instead of adding and doing the transformation, we do the transformations and then add. It should be exactly the same thing. So in this case, 6, 1, 2 becomes 6 plus 2 times this is going to be 8. 1 times 3 times this, because it's 1 plus 3 times this. So 1 plus 3 times this is going to be 9 plus 1 is 10. And what does the last one become? x3 becomes x3 minus x1. 3 minus 6 is minus 3. And we're going to have to add it to what this one becomes, which is 1 plus 2 times this. So 2 plus 2 is 4. X2, 1 plus 3 lots of this is going to be 1 plus 3 is 4. And x3 minus x1 is going to be 0, which is crap. So this becomes 12, 14 minus 3. 12, 14 minus 3. So I'm hoping I made a mistake somewhere along the way here. x3 is 3 minus 6, which is 3. Here it is 1 minus 2, so that actually should be minus 1, so minus 4. Sorry about that. That was a bit of a mistake. But as we said, these two things should be the same. So at least we've got a chance that this is linear. The other thing that can happen is that what happens to the transformation of 4, 1, 2, which is obviously 2 times that, or lambda times that. So if we 2 times this transformation, which obviously gets us back to this. So after the transformation, we're going to times it by 2. And what do we get? We get x1 plus 2 times this. So 4 plus 2 is 6. X2 plus 3x3. So 1 plus 3 times this is 1 plus 6 is 7. And x3 minus x1 is 2 minus 4 is minus 2. And obviously, when we multiply that by 2, we get back to exactly what we wanted, 12, 14 minus 4. So this is not a proof, obviously, because I've only used it for 1 point. So for this point, it looks like it's a linear transformation. To obviously prove it, we need to do it for x and y's, which becomes a little bit more substantial. So let's see. How would we prove it for this? And I'll try to be fairly quick. Okay, so let's look at the first one. We want to show that t of x plus t of y equals t of x plus y. Okay, so we're going to let x equal x1, x2, x3, and we're going to let y equal y1, y2, y3. And we're just going to add them together, basically. So if we just look at the left-hand side, tx is going to be x1 plus 2x2 plus y1 plus 2y2. The next one's going to be x2 plus 2x3 plus y2 plus 2y3. And x3 is going to be 3x3 plus 3y3. So what we've done in this case is we've just found out what the transformation of x is. And then we could add the transformation of y there. If we look at this side, what we're going to have is we're going to have the transformation of x1 plus y1, x2 plus y2, x3 plus y3. Okay, so when we look at the transformation of this, what we're going to get is the first one becomes x1 plus 2x2. So this is our x1, this is our x2, so it's going to become x1, or the first term, plus 2 lots the second term. The next one's going to become the second term plus 2 lots the third term. So the second term plus 2 lots of the third term. And the last one's going to be, the last term is going to become 3 lots of this, which is going to be 3 lots of x3 plus 3 lots of y3. And that now we're going to do what we did in lots of other occasions. Let's just rewrite this or reorder it, and we're going to get that this is x1 plus 2x2 plus y1 plus 2y2, x2 plus 2x3. But all we're doing here is really collecting the x's and the y's together, and this is still 3x3 plus 3y3.